Alright, dude, we are live. What's up, guys? This is Dem Keys, and holy shit, I took sort of an unintentional break. I haven't streamed in I think it's been 10 days, and it was not an intentional break. Dude, just stuff just kept coming up, and I wasn't able to stream. And especially like the past 3 days have been like just crazy busy for me. But the good news is all of that is done now, and now I can get back to streaming, which is great. I'm excited. In the meantime, it's not like I haven't been working on stuff. I've definitely been working on stuff. I finally managed to get I finally managed to set up the logic for getting the body pose landmarks into my VTubing application. I set up the logic for that. I did a bunch of testing as well. It looked great. I also had to change my messaging system a little bit to sort of accommodate whatever the requirements were. I'm being like super vague with it. I mean, I can best describe it by showing an example, and right now I cannot show the example. I was planning on doing a development stream where I was working on my VTubing app, but then I kind of got distracted with something, which brings me to what we are going to be doing today. Today, we're going to... Give me a second. My voice is being picked up way too well, and I love that. I mean, I'm seeing that in OBS. My voice is being picked up really well. I love that, but I need to make sure that it's not peaking. It's definitely not peaking, at least in OBS. I just need to... Okay, yeah, it's fine. It's great. We are good. So, yeah. I got distracted with something, which leads me to what we are doing today, which is we're going to be learning about neural networks. I have been learning deep learning on and off over the past couple of months. Whenever I get a chance, I'll dig into like different parts of it. And I'm still very much a beginner in deep learning. I don't know like too much about it, but I want to learn. And so I've been doing stuff. I've been doing a whole lot of reading. I also took out some time and watched some lectures from, I think it was lectures in MIT. They were doing a deep learning, I guess you can call it a deep learning course. But it wasn't just one thing. It was like it spanned across like it spanned across multiple lectures. So like the first lecture, it explained the idea behind deep learning. And wait, did it actually go into like deep learning itself, or did it jump into I think it jumped into neural networks. So the idea with deep learning is that it's machine learning, but very heavily focused on the use of neural networks. So you're doing machine learning. Deep learning is a subfield of machine learning, which very heavily includes neural networks. So obviously, when you're learning deep learning, then the first thing you should learn is neural networks, because it's sort of the basic building block of deep learning. And neural networks, the neural network itself as a concept has its own like basic building blocks, right? You need to know various concepts like what's a neuron or a perceptron, how input gets transformed in various ways, like what is a layer in a neural network, what are nodes, what are weights, what is training, stuff like that, right? So they have a bunch of lectures. It's a very useful, like, I'm glad that they did it, and it's like out in the open, like it's open source. So you have the course material available online. You have these lectures being uploaded to YouTube. Um, you have even like hands-on. Hold on, did the music like just stop? No. Okay, we're good. Hold on, dude. I hope it doesn't do the same thing it did the last time, where for whatever reason YouTube played an a very copyrighted music, a very copyrighted song, or YouTube played an ad that contained a very copyrighted song. I think it was the song itself that was being advertised, and for whatever reason that played, and well, I didn't find out until much later when YouTube's Content ID system picked it up when I tried to upload the VOD. Which kind of sucks because I don't listen to the music when I'm streaming. I have the music so that the stream can hear the music. So like I'm not always hearing what's playing, and as a result, I don't know if suddenly like I'm playing the stuff from this playlist, right? This playlist is marked safe for streaming by the artists who made these songs. They have made this playlist, they have added the tracks to it, so I'm taking their word for it, and they are, so far they've been good on their word, right? The music that I've been playing from this playlist is definitely safe for streaming. I'm able to play it during my streams on Twitch. After I get done with the stream, I don't have any situations where, parts of the VOD are getting muted or anything like that. Later on, when I upload the VOD to YouTube, I don't have issues where there's the Content ID system does pick up the music. It does say that there is copyrighted content, but it also says that the copyright owners allow it to be posted or used on YouTube. So even there's no issue. Like it's just the Content ID system is letting me know that yeah, this is copyrighted, but the owners, they allow you to use it. So I usually don't have an issue. The only time an issue happens is when YouTube just randomly decides to play a whole copyrighted song from somebody else in the form of an ad. And I'm not going to find out when they're doing that because I'm not looking at the, this makes me wonder if I should have actually that's kind of risky though. But yeah, it makes me wonder if I should have a small screen of the YouTube video that is playing. I could have it in some corner of the screen. And that way I would know when an ad suddenly starts playing. Because don't get me wrong, I have no problem with ads playing. I have a problem with an ad playing that contains a copyrighted track, which is then going to be seen as me trying to play copyrighted music from that artist during my stream. That's what I have a problem with. But anyways, dude, okay, that was a tangent. Okay, so today I was planning on working on my VTubing app. Okay, so just a quick thing with the VTubing app. Where am I at currently? So I have been I've been working on the whole mechanism. Previously, I'd built a messaging system. This was before I even set up the socket logic, which, by the way, I also implemented the socket logic, the networking logic in my VTubing app. So now we are able to have communication with external apps, which is great. And it's all being done using the C# tap model. So it's all being done asynchronously. What was I saying? Yeah, previously I'd made a messaging system that was gonna handle communication, and I'd also made a messaging protocol that was gonna it dictated the format of the messages that were being sent. And after some testing, like all of this was just on paper. This was all in theory, and I'd implemented the system. The thing is, I hadn't implemented the communication part itself. So I didn't realize that there could be certain issues that come with it. Which, to be fair, the issue that I found out later on, it was for a specific use case, like that specific use case. So, okay, the idea is with the messaging system that I built, it receives a message. It receives what's called a DVT MP message, and that's basically a message for the VTubing app, and it has its own format. It has like certain fields. The message that is received, it's going to be JSON data, and that JSON data has to be deserialized, and then we can do something with the data that we get out of it, right? This is great for like one-off things. Stuff like, oh, I wanted to trigger a push of something, or I wanted to do so and so, whatever. It's not great for situations where I'm having to continuously receive data. One very good example would be receiving body pose landmark data. If I'm receiving it almost every frame, then basically almost every frame I'm deserializing JSON data. And keep in mind, the JSON data is a string. So eventually there's going to be garbage collection happening. And I wasn't just doing one JSON deserialization, I was doing two because of the way that I'd set things up. Now, something I learned here is that when I'm designing the system, if the system is supposed to have communication or networking, then maybe I should also implement the networking and do a bunch of tests to see. But to be fair, I couldn't have seen this coming. There's too many things to think about. I usually with the use cases that I had in mind for my for the messaging system, like the body tracking data was one use case, but I had a bunch of other use cases, which I still have those use cases. For those use cases, my messaging system, my messaging protocol works fine because it's like a one-off thing, right? It's kind of like interacting with like a REST API where you hit an endpoint with a request and it hits you back with some kind of JSON data. Right. Okay. Now, I forgot where I was going with this. But anyways, I discovered that if I'm going to be receiving data every frame, and I'm going to be deserializing, if I'm going to be receiving body pose landmark data every frame, I need to find a better way of receiving this data, because receiving a bunch of bytes and then converting it to a string, which is going to be the JSON string, and then deserializing that string, and then doing another deserialization of a string that is made from a byte array that is within the data that has just been deserialized. There's a bit of a hierarchy going on if you didn't notice. Doing all of that stuff, like eventually, and keep in mind, doing this almost every frame, because I'm receiving body pose landmark data almost every frame. Doing this almost every frame leads to garbage collection happening, from what I've seen, every few seconds. I was noticing garbage collection happening like every 15 seconds, I think. I wish I was kidding about that. I would every 15 or at the very least every 30 seconds. I was noticing garbage collection happening. Like I would see a very visible freeze. And when I started seeing that freeze, I was like, what is going on here? Let me profile this for a second. I profiled it, and I looked at the point where, and like this is one of those situations where I've I just thought about looking at the profiler. I started the profiler, instantly I found the problem. I've never had that kind of a situation. I've had to like track down issues previously, but like in this scenario, I found it like within seconds, which I'm kind of glad about that. I didn't have to dig too much. Fortunately, there's like a whole bunch of information available in the memory profiler. So like, if you do want to dig, you can dig. It even gives you like a breadcrumb trail, so you can like track things down easily. That being said, I tracked it down and I found out, oh shit, garbage collector. The garbage collector was basically yelling at me because I was doing a whole bunch of like string related stuff, and it was happening every frame, right? That the moment I saw that, and I thought about what exactly I was doing, that's when I realized that the system that I built, the whole communications system that I built, it wasn't made for real time communication. It wasn't meant for continuous communication, like receiving data every single frame. It wasn't really meant for that. I can still use it for other stuff, but for situations where I have very real time, like data that's coming in like constantly, continuously receiving data, I need to take a more primitive approach and just work with bytes, which I'm okay with that. It's going to be a little extra work because I need to figure out a proper format, which I mean, I kind of like doing that. I've done that for a couple of other things in the past, uh, where you basically like just set up offsets for all of the various variable values that you want to store, and then you can create like a massive array and send data. So that's what I'm going to be doing. I was actually planning on streaming that, me setting up that logic. I have to set it up on the Python side and then set it up on the C sharp side as well. On the Python side, it's going to be so that I can send a, a big byte array from the media pipe script. Give me a second. I need to hydrate. I also just realized that because I haven't streamed for 10 days, or I think 11 days, I don't know. So I think speaking is going to be kind of rough for me. Though, I mean, I have spoken in the past 2 or 3 days. Like let's see. Let's see. I don't know what the situation is going to be. I hope I'm able to talk for a while because I do have time today. So I wanna make use of that time. I have a good like 2.5 hours more, maybe 3, and I kind of want to use all of that time. Okay, so yeah, one of these days I'm going to be doing a stream where I set up the logic for, what I've noticed, like if I just carry on doing my work off stream and I don't worry about doing it on stream, I'm able to make like a lot more progress because I'm doing the work then regardless whether I'm streaming or not. And so far, I mean, I've had that philosophy for like a while. I usually don't pause the work uh, just so I can do it on stream. I carry on the work even off stream. One exception that I made was with the hand gestures, the hand tracking thing, specifically hand landmarks. That thing is kind of, it's still incomplete. Like I did that stream. I don't even remember when. I think that was the last stream that I did. I think that was the last stream that I did. And after that I just got so busy. Believe it or not, I said on stream that I'm not going to be touching this off stream. I didn't touch it off stream. Problem is, I just didn't touch it at all after that because I kept waiting for the right time to stream it, which it's a horrible approach to take. And I'm glad that I usually don't do that because like I learned a long time ago that doing that is gonna really hinder my progress. Whatever work I'm trying to do, whatever I'm trying to build, the progress is going to get hindered. As much as I would love to show all of the progress happening on stream, believe it or not, a lot of it happens off stream. A decent amount of it happens off stream. Just like the progress on the VTubing app, I implemented socket stuff, async sockets. I implemented the body pose tracking stuff, the body pose landmarks, and next I'm gonna be implementing. I'm not sure what to call it. Like real. Okay, yeah. Hold on. So another change that I'm gonna be making in my communication protocol. I decided to introduce a new type of message. So how it's going to work is, so previously what was happening was the VTubing app would receive a byte array. Like that's how sockets work. Like they send and receive bytes. So the socket would receive a byte array. That byte array is supposed to contain the JSON text. It contains the bytes. I need to decode that into a string, and that's then going to contain the JSON text. The JSON text is basically data for an object. Hey, Matic, welcome to the stream. How's it going? Uh, can I help you with the code? What code are you talking about? So yeah, like I was saying, I what was I saying? Okay, yeah. So that entire that JSON data is supposed to be it's supposed to be deserialized into a message object that's going to contain the data. And what I need to do now is take a different approach where I receive a raw message instead. That raw message will contain a big byte array. The first byte, I wrote a keylogger, but I can't install Pi input. Uh, I I've never installed Pi input myself, so I don't think I can help you with that. What what exactly you're saying? You cannot install Pi input if it's a Python script. What are you getting, like some kind of error when you try to install the package? Where was I? What was I saying? Oh, yeah. So the idea here is it's going to be a couple of bytes, right? Let's say 1, 2, 3, 4, 5. Okay. So let's say the raw message is 5 bytes, right? The first byte is going to contain a magic number, which is gonna specify what type of message it is. So this is a raw message. The raw message is usually going to be much bigger than this in size, but like for the sake of an example, I'm doing this. So the first byte is going to contain um, it's going to contain the magic number, and then that magic number is going to dictate what the rest of the bytes actually are. And so then I'm going to have a system that checks based on what the magic number is. It's going to handle the data separately. It's going to handle the data in a different way. Right. Now, I'm going to be doing that probably on stream at some point. I'm not sure. For today's stream though, the idea is to I'd started reading this thing. Um, hold on a second. Yeah, I'd started reading this thing off stream, but I figured it's around stream time, so I might as well read it on stream. I didn't realize it was this zoomed in. Damn. Wait, is it zoomed in? Or no, I don't think it. Yeah, okay, the zoom in wasn't too much of an issue. Wait, what is going on? This looks kind of different. Okay, maybe it just looks different to me. Okay, so I was reading this. Also, this is kind of funny. I so I've used matrix multiplication in the past, right? I've used it when I was doing stuff with shaders. I used it quite a bit when I was doing stuff with shaders, and that was one of the situations where I had to actually learn how to do matrix multiplication because I didn't really learn it in school. So I learned what matrix multiplication was and how it was done and what the rules were surrounding matrix multiplication. But the thing is, when you're doing it in graphics programming, you're not often faced with situations where you have to like manually do the matrix multiplication. Like, I mean, okay, maybe you might need to write a function that does it, but like generally you kind of have a function that you give two matrices to, and it just does the multiplication for you. So like eventually you just get used to that kind of workflow. So even though I had learned matrix multiplication when I was learning stuff about shaders, I eventually forgot about how like, I forgot the rules because I wasn't doing it. I wasn't doing the matrix multiplication on paper as often because like you don't need to do it. Usually there's going to be a method, a function, a library, or usually there's going to be a library with a function that allows you to do that because it's so much faster. You don't have to do it by hand. But like you do have like select few scenarios, especially with like learning scenarios like what I'm doing right now, where doing it by hand can help you. It can help you understand things a little better. It can help you, or at least it helps me visualize things better, and it helps me with like testing situations as well. So I'm gonna have to. My point with saying this is that I'm gonna have to revisit matrix multiplication again, which is why I have the thing over here. I think for the most part I've gotten it. I know that the one of the rules for matrix multiplication was that the number of rows of the first matrix must match the number of columns of the second matrix, otherwise the multiplication cannot take place. I need to look. I need to see what the rules for addition are. But yeah, so I know that's one of the rules. There was this really helpful video that somebody had done on which that to be clear, that video it basically described this what's going on here. It basically described this line, but that person put it in like this is described in like a very mathematics kind of way, right? That person just did the whole thing on a whiteboard, and they showed visual patterns. It was a very visual learning experience. Let's put it that way. And that was great because that helped me, and it actually helped a lot of other people connect the dots in the right way to where they were able to then just do matrix multiplication. And well, okay, so once you learn matrix multiplication, you then also learn something very important about matrix multiplication, which is that it is really tedious to do it on paper, to do it by hand, which is why you usually want to write some kind of program to do it. You usually want to write some kind of code to do it. And I discovered that after I started learning how to do the multiplication. But I had to learn it. I'm still glad that I learned it, because doing not doing learning matrix multiplication, it helped me understand how I was getting the results that I was getting, because otherwise I wouldn't be able to understand. So one example of where matrix multiplication still is actually very heavily used, is in vertex transformation in the shader. So with shaders you have like with shaders you have multiple. Okay, there's going to be an ad starting soon, just heads up. Okay, with shaders you have multiple programmable stages. One of them is the vertex stage. This is a stage where you do vertex transformation. Any calculations that are supposed to affect a specific, or not a specific, that are supposed to affect all the vertices. You do these operations there, and it executes once for each vertex, if I'm not wrong. So that's how you're able to do the calculations for each of the vertices. Now, in this stage, this is where you do your transformation from object space to world space to clip space to eye space. So your object space is it's the space relative to the object that you're trying to render. Okay, there's an ad playing, so I'm gonna hydrate. Okay, welcome back. I think I got the order mixed up. Okay, so it goes object space to world space to what's called either eye space or camera space, and then it goes into I think then it goes into clip space. Let me just Google that so I'm not giving wrong information, because I've gotten the terms mixed up. I haven't done that stuff in a while. Hold on. Vertex transformation, DirectX. I could look at OpenGL as well. That's not an issue. But I just need to look at the stages, like what the names are. Because like, okay, the idea is you have the object space, which is a space that's relative to the object itself. So the origin is the object. It's not the world. The world has its own origin. Every object in the world has its own origin as well, in object space. So any vertex positions that are in object space, their positions are going to be displayed relative to the origin of the object itself, right? So you transform this into world space. That's your first transformation that you do. At this point, the vertex positions are now relative to the origin of the world. So that is how far away they are from the center of the world. And then you transform those world positions, those world space positions, into what's called, I believe it's called I think it's what exactly there was a name for it that is basically the idea there is you are placing the camera, the quote unquote camera, at the center of the world, at the origin, and then you're transforming everything else in the world in a way that makes it look like the camera is looking at them. So to give you an idea, actually let me get the proper name. I'm blanking on this big time right now. Hold on. I just need to get those terms and then it'll come back. Okay, so it's world space. It's object space to world space to camera space. And then there's a couple more transformations that happen. So like once it's in the camera space, you've basically placed the camera at the origin and you've moved other vertex positions here and there to make it look, you create the illusion that there's a camera moving. So to give you an idea, let's say you're playing, let's say if you're playing Minecraft, for example, and you're moving around, right? If you see objects, or let's take any, I don't know exactly how they do their rendering, but like just imagine in Minecraft, you're moving around, like you think that you are moving around, right? There's a camera moving around in 3D space. In reality, what's happening is during this stage, the vertices, the camera gets set at the center of world space, or well, yeah, I guess center of world space. The camera gets set at the origin and everything else gets transformed relative to the camera. And it gets transformed in such a way that you're able to create the illusion that there's a camera moving around. So let's say if the player or the camera is taking a step back, yeah. Let's say, I was just thinking for a second. So let's say the player is taking a step back and there's an object in front of you, right? So if you're taking a step back, the object is moving far away from you, right? Or you are moving far away from the object. But in reality, you are stationary and the object is moving further away from you. But you create the illusion that you are moving further away from the object, or you create an illusion that the player is moving further away from the object. And then there's another transformation that happens. I believe at that point is when they do the projection transformation. Not projection. There was another. Yeah. That's where they do the projection transformation. And then there's I think one or two others that happen, but those you don't necessarily control them. Okay, I forgot why I was talking about this. Oh, so yeah, all of this stuff, all of these transformations are done by multiplying vertex positions with matrices. So in short, you are doing matrix multiplication, a whole lot of matrix multiplication over there. And that is one of the reasons why I wanted to learn matrix multiplication, so I could do these calculations myself and understand exactly what is going on. Because because of doing this, I was able to understand exactly how a transformation matrix can be used to, let's say, move an object or move a vertex, scale a vertex, or even rotate a vertex. I learned how exactly rotation matrices work? What exactly do they do? So it was really interesting learning all of that. I don't remember how I got on this tangent, but yeah, uh, matrix multiplication. Dude, I knew there were 4 stages. So you have okay, model, view, projection. Yeah, okay. So those were the 4 stages, and the others then happen like either like they are done for you, or they happen like in the hardware, which again done for you. Like certain things do happen like in the hardware itself, so you don't necessarily always control it. But yeah, I believe it was these 4 stages. You can convert from object space to world space, from world space to view space, which is basically where the camera is at the origin of the world. Dude, I was trying to explain this shit, but just because I couldn't remember those terms, I just confused the whole thing. So you go from object space to world space, and from world space to view space, which is basically where you place the camera at the center of the world, and then you move, rotate, and scale everything else in the world, so that it creates the illusion that there is a camera in the world that is looking around. And after that, you do the projection transformation as well, which is where well, is it called projection matrix or perspective? Because what it's changing is the perspective. So you can have, I forgot what it's called, but okay, you have two of the most common ones. Two of the most common types of projections are your I think it's called perspective projection, and then you have orthographic projection, or is it? Hold on. DirectX perspective projection matrix. So it's a projection transformation, which you then have perspective and orthographic. Orthographic is more of your it's more of an isometric kind of thing. Not exactly isometric, but I'm not sure how to describe it. But you don't have like a 3D kind of situation going on where things are like skewed and stretched in different ways to give you the illusion of like 3D. Anyways, dude, okay. So I'm going to be learning matrix multiplication again. Just so that when I'm learning about neural networks and I want to do any of the stuff on, wait, is this a paid thing? This is a different article. This is not the same one. Okay, so this is different, and fortunately it is not paid, so that's great. But for now I'm reading this one. What is this? Oh, this is okay. All right, that's okay. Oh, man. I was supposed to start reading. I was supposed to start learning this stuff, but like we are 45 minutes into the stream and I've just kept on talking. I'm okay with that. Honestly, I'm okay with that. Fuck, dude, I haven't streamed in like 10 days. So I want to talk. That being said, let me hydrate real quick, and then we can carry on reading. I already read a good bit of this previously, so I'm not going to be reading that again. If you do want to learn this same thing, just Google this, Introduction to Neural Networks Part 1, and add the word medium in your Google search, and it should pop up. It is by this person, Harsha Bomana. So yeah, Hold on. How many? So this seems to be part of this thing. So let's open this up. If my mouse wheel stops misbehaving. How are we doing on music? Give me a second. Okay. We are good. You know what else I could do to maybe remedy the little YouTube mistake where they play a whole copyrighted song in an ad? Something else I could do is just wait for Twitch's own content ID system to pick up the song. Sometimes it can take them some time. Usually it's pretty quick, but I think that's for more well-known songs. I don't know how well that works out for brand new songs or for lesser known songs. Songs from like other parts of the world that, let's say, aren't the western side of the world. I could wait for a little bit. Usually what I do is like shortly after I'm done streaming, I'll start downloading the VOD. Because like I have to download it and then set it to upload, and the upload itself, it takes a while. Like I have to, it uploads and then there's processing that happens, and like all of that stuff. In all, it can take a good like 1 hour, if not a lot more. Which is fine because it's not like I get stuck. I just have it on a different tab, and then I carry on with whatever work I'm doing. So it's not that big of an issue. But yeah, I'm wondering if, like, would it help if I just give Twitch some time to pick up the song, or if I just give Twitch's content ID system some time to pick up the song, and eventually it'll pick it up and it'll mute that segment of the VOD. That being said, let's begin. So I read a good bit of this. In this first part, this person actually, they explain neural networks, but from like the human brain perspective. And it's an interesting read. Then slowly they go into the conceptual idea of a neural network, which is this. They're explaining that you have multiple layers in a neural network, and each layer has multiple nodes, and each node in each layer is connected to every node in the next layer, which is being demonstrated here. And then they go into the perceptron, which is basically your node. And here they're demonstrating that your input values, they're multiplied by the weights. And then there's a bias value as well, which I later on learned that apparently it's great. It's great if you want to add some sort of, if you want to tweak things a little bit. So if you want to, you have that option, but you don't have to. So if you don't want to do it, you can just leave the bias to like a fixed amount, which, because it's addition, so I'm guessing you would then be leaving the bias at 0. Wait, you add the bias, right? You don't multiply the bias? Yeah, okay, you add it. So yeah. Oh, and then the final value that you get, you pass that through an activation function. And that value that you get is what gets sent into you know the further that value basically gets used in further computations. Let me put it in that way. So I was over here where they showed this diagram, and then they explained over here that these values were the result of the multiplication of the input vector with the weight matrix plus the bias vector. All right. The weights in this case have been color-coded for easier understanding. We can represent the entire calculation as a matrix multiplication. If we represent the weights corresponding to each input node as vectors and arrange them horizontally, let me read that again. If we represent the weights corresponding to each input node as vectors and arrange them horizontally, we can form a matrix. This is called a weight matrix. Now we can multiply the weight matrix with the input vector and then add the bias vector to get the intermediate node values. So I guess this is the part where GPUs become useful here, because GPUs are good at doing matrix calculations like very quickly, and like these days, actually for a good couple of years now, you have like dedicated cores for doing these kinds of calculations. I believe that's where tensor cores come in, but like I think they can do a lot more than just this. But yeah, this is also something that they do like really well. And this is not just one calculation. Throughout that entire neural network, you're going to be doing tons of similar calculations. So like if you are able to parallelize it, basically running it on the GPU, then that's like a massive speed boost, because the GPU can do multiple of these calculations in parallel and give you a result much faster than if you were doing it on the CPU. Though, I mean, that would really depend on the setup. That's not always the case. It would really depend on the setup. But generally, like that is the situation. Or that is the case. Okay, so here so the value before passing it to the activation function is called an intermediate node value. Okay, interesting. So then that intermediate value is passed through an activation function, which we'll get into activation functions as well. By the way, I had learned this stuff when I was watching the MIT lecture. Huge shout out to those people, by the way. Like, I'm glad that they decided to put those lectures up on YouTube. Sharing the knowledge with everyone. And there's like the study material, the slides that they use, all of that stuff. It's available online. There was even a labs segment. I think they were using notebooks or Google Labs or something else. I don't remember I think it was some form of notebooks. Either it was Google Colab or it was Jupyter Notebooks or it was something else that supports notebooks in some way. I can't remember what it was exactly. Okay. We can summarize the entire calculation as so and so, so and so, so and so. All right, great. Here, y is the output vector, x is the input vector, w represents the weight matrix between the two layers, and b is the bias vector. we can determine the size of the weight matrix by looking at the number of input nodes and output nodes. An m by n, or m multiplied by n weight matrix. Oh, it's m by n. Okay. An m by n matrix, weight matrix, means that between the two layers, with the first layer have... No. Let's do that again. An m by n weight matrix means that it is between two layers, with the first layer having n nodes and the second layer having m nodes. Okay, hold on. So how would that work? Because like we are talking about multiplying one node with multiple other nodes. Okay, let's see. There must be a visual thing here. Okay, so number of columns, n, which is the number of input nodes. Number of rows, m, which is the number of output nodes. So we are representing this. I need to... Yeah, at some point I'm going to need to draw this out just so I can better visualize. Maybe I need to read that again. An m by n weight matrix means that it is between two layers, with the first layer having m. So it's talking about the entire layer, not the first node. It's talking about the entire layer. So an m by n weight matrix is basically describing the number of nodes in the first layer and the number of nodes in the second layer. So the first layer would be n. Oh, that's interesting. Okay, so the first layer would be n, which is the number of columns in the matrix, and then the second layer would be m, which is the number of rows. That would be the weight matrix. Okay, so I'm gonna need to do this calculation like at least a little bit by hand, so I'm able to like understand. I still need to be able to visualize it properly. Or maybe it's just because I haven't gone further into this that I don't get it yet. But okay. Now let's look at a complete neural network. By the way, we're going to be doing this for the next couple of streams, I think. Actually, I mean, I'm going to do this off stream as well. So, I mean, there's a chance that I might finish this. I don't think I'm going to finish this real soon because, I mean, I'm learning about right now we are learning about neural networks. I've learned a little bit, like, you know, separately as well. So I do know a little bit about neural networks, stuff like the fact that there's feed forward neural networks, recurrent neural networks, convolutional neural networks. I know about that. I also know that feed forward is like the most basic one that you can make, and that's what I'm aiming to make first. After that, I want to go for a recurrent neural network, and then a convolutional neural network. Once I've done these three, then I think I would consider that I've learned the basics of neural networks. Because after that, there's much more to explore and discover. But like once I've learned these three, I'm going to be able to apply neural networks to a bunch of other problems to try and solve them. Okay, I forgot why I was saying this. Oh, so I was saying that we are probably going to be doing this for the next couple of streams, which technically I guess it is true. Because, okay, I'm going to carry on reading this. I'm going to, there's going to be an example that shows up. I hope the example is for PyTorch. I haven't looked at the code yet. I really hope it's for PyTorch, but it could very easily be for something like Keras or what's it called, TensorFlow, or I don't know if scikit-learn has something for neural networks. It could be any one of them. Uh, Wait, let's look at the. Is there any code here? Oh, they don't go into the code at all. Okay. Oh, cool. They've got something for NLP as well. What more do they have here? Deep CV. How CNNs work. Holy shit, dude. They've got a bunch of things. Yo, shout out to this person. Yo, I hope like the stuff that at least I'm looking at isn't behind a paywall. Because otherwise I'm gonna have to like leave it and move to something else. If it isn't, like, dude, I mean, if it is, I'm not really shaming the person. Like, you do you. It's your content. You're the one putting it out. Great, awesome. But like, if there is gonna be a paywall, I would rather find out early on so I can go look at something that doesn't have a paywall. That's my point. Oh, okay, cool. So they have a loss functions thing as well. Loss functions come in where when you start doing training. Generalization in neural networks. Okay, okay. Deep computer vision. Oh, I like that they used computer vision to explain convolutional neural networks. Deep CV, advanced convolutional layers. Man, this person has like a bunch of stuff. That's crazy, dude. Oh, nice. They even went into recurrent neural networks. Yeah, eventually I do wanna go into like the NLP side of things as well. It's just not something I'm focusing very heavily on right now. Um, but eventually I will be going into that side as well. I need to go and explore the Transformers architecture as well. I Speaking of Transformers, I need to explore the Transformers library, the Hugging Face Transformers library, and the what is it called, Diffusers library from Hugging Face, because they provide you with like a bunch of extra features. For example, with the Transformers library, man, my speech. Hold on, dude. Give me a second. Let me hydrate. Okay, so one of the many things that Hugging Face Transformers, the Transformers library, allows you to do is it allows you to, let's say, you can pick a specific, just as an example, you can pick a task that you are trying to do. So let's say sentiment analysis. Let's say you wanna give it. Is that really the best one? No, let's say classification. Let's say you want to classify things within a sentence, right? So that's your task, classification. Then you can choose a model that will be that will be loaded from Hugging Face, and Hugging Face has a bunch of models. Like, this is sort of the hub for machine learning related stuff. You have people, all sorts of, like, the models aren't necessarily made by them. These are models contributed by the community. What Hugging Face does is they work on adding they work on how do I even explain this? They work on integration so that you can use these models very easily from their libraries. And that's great because you are then able to use the Transformers library to accomplish a bunch of different tasks. Let's say you wanted to categorize certain words from a sentence. You can specify the task as classification. You can specify a model as well. There's going to be a list of models that you can use. I believe you can also specify. I think data sets come in usually only when you're training, or there might be other scenarios as well. I don't remember, but yeah, you can specify a data set as well. And I believe they also have data sets hosted. They also have models hosted, so like that is how you're able to get access to it so easily. And like they're actively developing the transformers library. You see a lot of new ML models, deep learning models as well, coming out every now and then, and they're quick to, like Hugging Face, they're quick to add support for it to their transformers library. I haven't explored the diffusers library so far. All I know is that it has something to do with with not necessarily stable diffusion, but diffusion itself, which is another topic that I need to explore. I think it's called latent diffusion. But yeah, I need to explore transformers and diffusers. For now, let's carry on exploring this. Just a second.
يوتيوب بريميوم هو يوتيوب بدون إعلانات ويوتيوب ميوزك بريميوم جرب لشهر مجانا.
Just a second. All right. Okay. So okay. Let me just make sure the music is still going, and then we can carry on. Okay. Cool. Nice. Awesome. All right. Okay. So we were down here, I think. Yeah. Now let's look at a complete neural network. So this is what a complete neural network looks like. You have the input layer, the hidden layer, second hidden layer, and then the output layer. The connections between each of these nodes are the weights. Oh, it also mentions it here. The connections are the weights. So, okay, now I need to be able to visualize this. So the weight between each of these layers, you have a weight matrix. And so the input is then multiplied by the weight matrix. Is that how it's working? So it said m by n, right? For an m by n matrix, let's go back. Let me not try to remember the thing. For an m by n matrix, n, which is the number of columns, is going to be the number of input nodes. That is why it's a 4 by 3. Okay, because m is the hidden layer 1 and n is the input layer, or x, I guess. All right. Okay, hold on. Hold on. I'm trying to imagine, like this just occurred to me. Have I just never been I have to do this calculation on paper in order to figure out if this is actually like what is going on. Okay, hold on. So it's one weight matrix. The weight matrix is 4 by 3. If it's 4 by 3, we're going to have 12 connections. And we have 12 connections here, right? 1, 2, 3. No, okay. This is 4. This is 4. And then this is 4. Yeah, so we have 12 connections. So, like, is multiplying one layer with the other layer basically just one big, like, matrix multiplication operation? Because, like, that's kind of cool. Like, have I just not visualized it in that? I still don't know. I still don't know. We need to move forward with this for me to figure it out. But like I'm wondering if between each of these, between each layer, it's just like one big matrix multiplication operation that's happening. Saying matrix multiplication operation is just such a fucking mouthful, and for some reason I'm not able to. Well, I mean, I think the reason I'm not able to talk is because I haven't streamed in 10 days. So, like, any progress that I make, it kind of just dies out. At least with my voice, it kind of just dies out. But, I mean, to be fair, I'm doing relatively well in terms of how well my voice is doing. Because, like, usually I would start to feel like stress in the vocal cords within like half an hour to 45 minutes. Right? But, like, since I started drinking water every 15 minutes during my streams, I'm able to go for a little bit longer before the stress starts to, well, before the vocal cords start to get stressed. I forgot why I was saying this. Never mind. Let's carry on. So, so they broke down the entire calculation here. Why is this nested? Oh yeah, okay, because it's going from like from the input layer to the hidden layer 1 to hidden layer 2 and then to the output layer. That's why it's nested. Because they have to calculate this first. After calculating this, they then pass it to this and then pass it to this. So each of these are activation functions. All right, this is a small neural network of 4 layers. The input layer is where we feed our external stimulus, or basically the data from which our neural network has to learn from. By the way, I believe the person is using external stimulus just to sort of connect, like circle it back to what they were explaining here. Because when they were explaining how the neural network works in a human brain, or how neural networks work in a human brain, they did mention external stimulus. I believe they did, because like they mentioned like there is some kind of stimulation from the outside. One example they use here is touching. Well, okay, they mentioned external source. I don't know if they specifically used the word stimulus, but yeah, they did mention external source, and their example was with a hot pan. So they were explaining what exactly is happening in your brain when you accidentally like touch a hot pan. Okay, so the input layer is where we feed our external stimulus, or basically the data from which our neural network has to learn from. The output layer is where we are supposed to get the target value from. No. The output layer is where we are supposed to get the target value. This represents what exactly our neural network is trying to predict or learn. All layers in between are called hidden layers. when we feed the inputs into the first layer, the values of the nodes will be calculated layer by layer. Let me read that again. When we feed the inputs into the first layer, when we feed the inputs into the first layer, the values of the nodes will be calculated layer by layer using the matrix multiplications and activation functions. Hold on. When we feed the, and I'm trying to make sense out of this, the way that this sentence is formed. I don't know if I'm just reading it wrong. When we feed the inputs into the first layer, the values of the nodes will be calculated layer by layer using the matrix multiplications and activation functions till, I read that as still. Holy shit. Okay. Activation functions till we get the final values at the output layer. This is how we get an output from a neural network. So essentially, a neural network is, simply put, a series of, oh, there it is, a series of matrix multiplications and activation functions. When we input a vector containing the input data, the data is multiplied with a sequence of weight matrices. Let's read that again. When we input a vector, I'm reading it again just so I can sort of just absorb the information a little better. When we input a vector containing the input data, the data is multiplied with the sequence of weight matrices and subjected to activation functions till it reaches the output layer, which contains the predictions of the neural network corresponding to that particular input. Okay, so now we are moving on to activation functions. So I've read about, or well, I've read about, and I've even seen in the videos that I had watched, they explained that it makes an activation function is basically a way of making the operation non-linear, or making the value non-linear, and that's fine. Like, theoretically speaking, okay, I kind of get it, but I need to do this in practice to see the result, or rather I need to do this on paper to see the result. I think I should do this on paper, because, like, okay, let's say I do this kind of a neural network, right? And I try to solve, because I feel like this kind of a neural network, I can do this. I feel like I can do this on paper. It's going to be fairly big, because fucking look at these matrices. It's going to be a fairly big calculation that I would have to do, but I can do it. And once I do that, assuming I've done it right, then okay, I just saw the word non-linearity mentioned here, and now I cannot remember if earlier I said that activation functions make the result non-linear, or I said linear, because I meant to say non-linear. I believe I said non-linear, but like if I said linear accidentally, just let me correct myself. Non-linear. Okay. Carrying on. I need to do these calculations on paper. I wonder if I could like do it with like a much smaller neural network, just for the sake of an example. So let's say 2 input nodes, 3 hidden layer nodes, 1 output node, and then I can like see the result that I get. Okay. Role of activation function. Actually, I need to hydrate, dude. Give me a second. Okay. Role of activation function. Even though our neural network has a very complex configuration of weights, it will not be able to solve a problem without the activation function. The reason for this lies in the concept of nonlinearity. Let's revise what linearity and nonlinearity means. Okay, so we have an equation here. The above equation represents a linear relationship between y and x1, x2. Between y and x1, x2. Regardless of what values w1 and w2 have, at the end of the day, the change of values, the change of value of x1 and x2 will result in a linear change in y. What if we look at real world data? No, now if we look at real world data, we realize that this is actually not desirable because data often has nonlinear relationships between the input and output variables. Okay, so this is what well, yeah, okay, that I keep forgetting that linear is usually in a straight line. I keep forgetting that. Even though like I've done math with like linear stuff. For example, LERP, linear interpolation, that usually follows in a straight line as well. It's not generally curved. But like I mean you can use it in different ways, but that's an example. LERP, I said LERP as if I was doing like a Unity development stream. It's just an old habit because like I've used LERP quite a bit. But yeah, LERP is a function in Unity. Mathf.lerp, which is basically linear interpolation. Okay, the above diagram represents a typical data set which shows a nonlinear relationship between x and y. If we try to fit... Wait. The above diagram represents a typical data set which shows a nonlinear relationship between x and y. Okay. Alright. If we try to fit a linear relationship on the data, we will end up with the red line, which is not a very accurate representation of the data. However, if our relationship can be nonlinear, we are able to get the green line, which is much better. Now let's compare the neural network equation with and without the activation function. Alright. Okay. Okay, so the only difference I'm seeing here is that it's within an activation function. Yeah, I'm trying to find something else, but like there isn't anything else. Okay, we can observe that in this equation there exists a linear relationship between the input and the output. However, in the case of the equation with activation function, we can say that the relationship between input and output can be nonlinear. No, let me read that again. However, in the case of the equation with the activation function, we can say that the relationship between input and output can be nonlinear if the activation function is itself nonlinear. Hence, all we have to do to keep some nonlinear functions as to keep is hence all we have to do is keep some nonlinear function as the activation function for each neuron, and our neural network is capable of fitting on nonlinear data. Let's take a look at a couple of popular activation functions. Okay. Yeah, I've seen both of these. I haven't tested them out myself yet. So ReLU stands for Rectified Linear Unit. It essentially becomes an identity function, y equals x, when x is greater than or equal to 0, and becomes 0 when x is less than 0. Wait, so basically if it's less than 0, then it's 0, but if it's greater than 0, then it's the same as whatever the other value is? This is a very widely used activation function because it's a nonlinear function and it is pretty simple. Okay, what if we applied that here on this graph? Would that still work? Like, I mean, doesn't that make it linear? Maybe I'm just imagining this the wrong way. I need to do some like examples. Okay. Oh, real quick, let me just confirm music is still going. All right. We are good. Great. Sigmoid. Sigmoid is essentially a function bounded between 0 and 1. It will become 0 for values which are very negative and 1 for values which are very positive. Oh, is that what it means? Bounded between 0 and 1? So it'll either be 0 or it'll be 1? Hence, this function squishes values. Okay, so it's clamping values which are very high or very low to the values between 0 or 1. This is useful in neural networks sometimes to ensure values aren't extremely high or low. This function is usually used at the last layer when we need values which are binary 0 or 1. Okay. This concludes this part of the tutorial. Okay. All right. Cool. Nice. All right. So we can move on to the next part. So I'm going to explore activation functions later on, because like I get the idea behind the functions, but I need to explore them more to, for this stream I probably should have expanded. Maybe I can do it now. Give me a second. I probably should have just used the I probably should have just had the give me a second. Yeah, I probably should have just had the browser thing as the full screen instead of having VS Code. I thought I would be going into a little bit of code today, but like I'm for the past like 1.5 or 1 hour, I guess, I've just been reading the thing. Desktop, okay. Then Okay, I think I can disable both of these and have this third one be this one. Yeah, this should this should be good. And it seems like I've cropped it properly as well. So that's a plus point. All right, great. Cool. Okay. Okay. So, moving on. Back propagation. Now that we have a neural network, no, now that we have seen how a neural network is, oh, there's an ad. You know what? I'm gonna hydrate. All right, welcome back. So, back propagation. Now that we have seen how a neural network is represented, we can go on to see how exactly it works. Since there are many layers having many neurons, there exists a complex set of weights to get an output. Oh, this is where they are telling us how those weights are actually generated. Where was I? But yeah, okay. So once again, having learned some of this stuff before from other sources, this it gets really interesting here because here you get to see. I believe both the weights and the biases get generated during the training process. I believe so, and maybe some other stuff. We'll see. I guess it would depend on the situation, like what kind of stuff gets generated. Okay. Uh, where was I? Since there are many layers, having many neurons, there exists a complex set of weights to get an output from some input variables. Each weight in this network can be changed, and hence there are countless configurations a neural network can have. A trained neural network has some weights configuration which accurately predicts correct outputs for some input data, and we'll now go through how exactly a neural network trains itself. Okay, that was weird. OBS disconnected for a bit. Well, my connection had a little hiccup. It wasn't really OBS. I don't know if the issue is going to return again. Hopefully it doesn't. But hey, on the bright side, at least I got to stream for an hour and a half at the very least. Hopefully we can go for longer, but like, just in case something happens. This was fun. Okay, a trained neural network has some weights configuration which accurately predicts correct outputs for some input data, and that is what we hope to achieve. We will now go through how exactly a neural network trains itself to get this wow, that is not easy to say, to get this desirable weight configuration. Backpropagation is the name of the algorithm a neural network uses to train itself. This revolutionary algorithm is a mixture of the chain rule in derivation and gradient descent, which is a common optimization algorithm which is used in linear and logistic regression. To understand how backpropagation works, we first have to understand the relationship between the output and the weights in between. It is clear that every weight in the neural network will affect the output in some way due to the way the neural network is connected. It is clear that every weight in the neural network will affect the output. That makes sense. Yeah, that makes sense. Because every node is connected to every single node in the next layer. Like each node in the previous layer is connected to all of the nodes in the next layer, right? So the weights definitely affect the thing along the way. Due to this fact, we can say that if I change a particular weight, the output will change in the same way. No, the output will change in some way. That makes sense. We can also find the exact mathematical equation defining the relationship between each weight and the output. Okay. Let's say we are given a data set with 3 input features, x1, x2, and x3, and we need to find the relationship between the input features and the output using a neural network. We will now see what exactly the neural network does. Wait, now, what did that say? And we need to find the relationship between the input features and the output using a neural network. Okay. Wait, so are we using a neural network to find the relationship? Or are we finding the relationship between the input features and the output that you get when you use a neural network? I think. Okay, so fortunately, I think we are back. Fortunately, we are back. The connection disconnected again, and well, luckily it connected before the disconnect protection ran out. I want to try and stretch this to like 20 more minutes. I don't know how well this is gonna hold out, or how much longer this is gonna hold out. But like, anyways, let's carry on. First, we feed in the data and get the output from the neural network. Okay, so that's when we use random weights. We shall call output y prediction, y pred. Next, we should compare the predicted value with the actual value. So that's where we get the loss or the error. This value will be called the error. It is essentially how bad or how far off the model is from predicting the values correctly. Our goal now is to minimize the error. Okay, that makes sense because you want to get the prediction to be as close to Oh man, it starts it starts to become a slideshow after I think after disconnects start. That's when it starts to become a slideshow. Now let me just look at OBS real quick and see if we are like losing frames or something, like actively losing frames. I don't think we are. I don't think we are. um I wonder, what if I close my application and open it up again? Okay, that should be good. Now I think I need to transition. No, I don't need to. I don't need to transition. The music seems to have stopped. Let's make sure. Okay, cool. Right, so we are good now. Great. Oh, this makes me think that I might need to introduce some kind of either, well, yeah, either some kind of like did some kind of disconnect protection in my VTubing app, or I mean, to be fair, I could just restart the app, like, because in these kinds of situations where the network connection just dies, even the connection to external apps that are like running on a system across the network, even that connection is going to die. Though to be fair, I mean, it's I'm using connectionless. Okay, I just realized. Yeah, okay, I'm using a connectionless protocol, so I guess that's not going to be an issue here because the socket is just going to keep. Well, no, hold on. If the connection dies, the thing is not gonna like. It's gonna raise an exception. I think it's gonna raise an exception. Yeah, I think so. Either way, like if that, yeah, dude, no, I'm gonna need to create some kind of mechanism with which I can detect when some kind of exception has been, well, I mean, there is, I can detect when an exception is raised, but like what to do at that point when the exception is raised, that's the important part. How should I handle that? The most simplest way to do it is just close the program and open it up again. It's like it does not hinder anything at all, and it literally only takes me like 30 seconds to do. So it's not that big of a deal, but like if I have some kind of system in place that can be heavily affected by the disconnect, then I might need to do something. But like generally, something that I don't have something that persists across multiple sessions. Uh, so like I definitely don't have something that persists across multiple sessions that could be affected by network stuff. So I think I'm good. Let me hydrate and then we can carry on reading. Okay. Where was I? You know what's interesting? I never learned calculus. Like, I don't know anything about calculus. I'm saying that because partial derivatives got brought up. I never learned calculus. I've been wanting to learn it, but it's one of those situations where like I don't learn it unless I'm really curious about it or I actually need it. Like, for example, I didn't learn. Dude, forget about linear algebra. I didn't even learn trigonometry in school because my education was kind of complicated. So while I did have an education, because of how complicated it was, my education of math stopped after 8th grade. I carried on. I carried on studying the other stuff, but math specifically, it stopped after 8th grade. And because of that, I missed out on like a bunch of subjects that a bunch of math related topics and subjects that I would have otherwise learned. And so I I didn't really learn trigonometry and linear algebra until years after I finished school. I basically learned linear algebra and trigonometry once I got into game dev, and I did that based on need because I needed to learn so I could understand game dev related math. So this is another one of those situations. Calculus as well. I just never learned it. So whatever it may be, integral calculus, differential calculus, and whatever other type of calculus exists, I don't know any of it. But if I need it for this, then I'm definitely willing to learn. Because like if I'm gonna need to calculate this shit on paper, then okay. So by the way, I keep saying on paper. I just mean like if I ever need to do it manually, I won't necessarily always be doing it on paper. It might just be I might open up, you know, a notepad and or maybe like a Python thing and like just do the calculations there manually. But like the idea is doing it manually. All right. So since ypred is a function of all the weights in the model, oh yeah, because it's a prediction, yeah, and error is a function of ypred. Okay, because you're getting error by seeing how far ypred is from y. That's an interesting, like I'm not used to calling something a function of. So like I'm when I read that each time, I'm just trying to imagine it so I can like grasp whatever is being said here. This means that we need to adjust our weights in such a way that the error is minimized. We do that using partial derivatives. Are they going to bring up like gradient descent here as well? Because it got brought up previously as well. Gradient descent is it's one of the methods that's used in minimizing loss. There was a name that they had given for minimizing loss. What was the name? I forgot. There was a term. I can't remember. Okay. Let's take a simple equation. Let's take a simple equation. No, let's take a simple example of an equation. Y equals W1 multiplied by X1 plus W2 multiplied by X2. If we find the partial derivative of W1 or W2 with respect to Y, we can find. One of these days I should do a stream where I learn calculus, or at least the parts of calculus that are relevant to machine learning. At least those parts, because like, dude, calculus is a massive subject. It's a massive thing on its own. It has like subfields. In fact, even integral calculus and differential calculus have like their own subfields. So like I sure as hell am not planning on learning all of that shit. I'm not even interested in learning all of it. I mainly only want to learn what I require. By the way, I'm starting to notice now that I'm having trouble talking, which is great. Like I've lasted for almost 2 hours being able to talk, and this is after not streaming for 10 days. So like I'm glad that my voice was able to keep up for or hold out for however long it did. Anyways, if we find the partial derivative of w1 or w2 with respect to y, we can find out how w1 or w2 can affect y. If the partial man, holy shit, this is not easy to say. If the partial derivative, that is not easy to say, dude. Holy shit. Of w1 with respect to y is positive, this means decreasing the weight will decrease y. Will decrease y? Isn't y fixed? Isn't y the... Wait, no, okay, y is... Hold up. Oh, okay, so we are looking at y, probably not this y. We are probably looking at the y here that's relevant to this simple example. Okay, so if y is positive, this means decreasing the weight will decrease y. If the partial derivative of w1 with respect to y is negative, that means increasing... Oh, so it's flipped. So increasing the weight will decrease y. It's not flipped. Hold on. Well, I mean, yeah, technically flipped, but like I probably shouldn't use flipped here. So if it's negative, then that means increasing the weight will decrease y. Okay. Is y supposed to be the output value, the expected output value, or the predicted output value here? Y is equal to so-and-so. Okay, anyways. Negative partial derivative and positive partial derivative. Man, it's great that I took the time to learn about matplotlib, because visualizing a bunch of these things, you need graphs for that. Definitely. At least the simpler ones, you need graphs for visualizing them, and stuff like this, it's going to help for me to know how to use matplotlib. Well, there's that, and NumPy and pandas. I'm glad that I took the time to learn those as well, because those are definitely used in like a bunch of other things that I'm doing. Funny enough, even in some non ML related things, it's also used there. Okay. These two rules are all we need to optimize the weights in the neural network. We need to find the partial derivative of every weight with respect to the error. If the partial derivative is positive, then we decrease the value of that weight so that the error is decreased. If the partial derivative is negative, then we increase that weight so that the error gets decreased. Wait, why did I change the inflection there? Okay, if that partial derivative is negative, then we increase that weight so that the error gets decreased. So okay, then we increase that weight. So I put the inflection on the... Well, no, not inflection. I put the emphasis on the wrong word. Okay, this is the basic underlying concept of how weights are updated after we calculate the error. Since the last layer is... Why is this highlighted in this way? Okay. Since the last layer is the closest to the error, we will first derive the last layer with, oh, is that why it's called back propagation? Because you start from the last and then keep taking steps back. Since the last layer is the closest to the error, we will first derive the last layer with respect to the error and update those weights. We will then move to the second last layer to do the same, and so on and so forth. We repeat this process with each, no, we repeat this process till we reach the first layer. Till we reach the first layer and all weights are updated. This entire process is called backpropagation. Okay. Derive and update, derive and update, derive and update. Okay. And then you run the calculation again. And then based on the results, you backpropagate again. And then you keep running this thing until you get the desired weights. Okay. Or until you get the desired error. We perform backpropagation for a single row of data and update the weights. We then repeat for all the data available in the training data set. This entire cycle is called one epoch. Okay. I still don't know how this word is meant to be pronounced. I just say epoch. I need to look this up on YouTube if there's like some other pronunciation for it. I could just be pronouncing it completely wrong. Anyways, for now I'm going to call it epoch. Usually neural networks. So okay, that's interesting because I've seen the word epoch in, man, now I'm curious if I'm actually pronouncing this shit right. Give me a second. Just a second. Enjoy the Grammarly ad.
In British English and in American English, and what is its meaning in epoch? For the purposes of chronology,
Epoch.
periodization is an instant in time choosing as the origin of a particular kind of that serves as a reference point for more.
Okay, so it's not epoch, it's epoch. Well, let me hear somebody else's thing as well. Where is it? The epoch. Epoch. Okay, holy shit, dude. Well, I mean, I was kind of close, so yay me, I guess. So epoch. So I've seen the word epoch being mentioned in a bunch of the code that I've seen. And usually that's the name that they give to each of the iterations, because like you do this continuously, right? And like they give like a limit for how many iterations they're doing. They call the iterations epochs. Okay, usually neural networks can take several epochs to train, and it is up to us to decide how many epochs it will train for. Okay, error calculation methods. Error is a very important part of A very important part of a neural network because it allows us to estimate how poorly the model is performing, and accordingly, we can update our weights to improve performance. Now let's go through how exactly error is calculated in neural networks. The type of error calculation method we choose will depend on the type of task we are trying to do. There are mainly two types of tasks a typical neural network can do. Regression or classification. Regression is when an output variable is continuous in nature. When y is a numerical value, which we have to predict, the task is called regression. Examples include trying to predict house prices or trying to predict how many marks someone will score in an exam. Classification is when our output variable is discrete in nature. When y is trying to represent a certain class out of a defined number of classes, the task is called classification. Examples include trying to predict between a cat and a dog, or trying to predict whether an email is spam or not. Give me a second, let me hydrate. Okay. Here we have to understand that in the regression graph, the output variable is a continuous value, just like x. In the classification graph, there are two input variables, x1 and x2, and the output is represented by the color of the points. Okay. Let's first cover regression. For regression, the error function we use is mean squared error. We are simply trying to find the difference between the actual value and the predicted value and then square it. The formula is given below. Okay. Here, E is the error of the model. Ypred is the output of the model for the data. And y is the actual output, which we are supposed to get. We squared this so that the negative and positive differences both become positive in the end. N represents the number of data rows we input into the model. Okay. We are essentially calculating error of all points and averaging them. As we train the model to achieve a very low, at some point I should do this calculation myself. I should also look into, I looked into both regression and classification when I was learning about machine learning. More specifically, when I was learning about supervised machine learning, I had learned about regression and classification, but I never fully understood what exactly I was learning there. Or rather, what exactly, how do I say this? I didn't really go too deep into it, but I feel like now I should, because I think both regression and classification have multiple methods, multiple ways that you can do them. And I think somewhere in between all that, I would just get lost every single time. And then I would just not explore any of them. Because like when you go for learning, when you start learning machine learning and you find out that you learn that there's supervised learning, unsupervised learning, and reinforcement learning, then under supervised learning you're gonna have this kind of stuff. At least for like labeled data, you'll have this kind of you'll have these kinds of techniques. There's regression, there's classification, and there's actually a bunch more. I believe so. No, wait. I think these both of these methods have multiple other methods to accomplish them. Both of these tasks have multiple methods, multiple different ways that can be used to accomplish them. So maybe I should look into them again real quick and like try to use at least one of the techniques. Okay, hold on. Okay, yo, I'm I'm getting tired. Um so I think I'm going to end the stream here, and I might stream to I don't actually know if I'm going to stream tomorrow because I'm going to be busy with something tomorrow around stream time. Maybe I might stream. I don't know. But yeah, I'm going to carry on reading this. Hopefully I'll be done off stream. Like I'll be done reading this. They have done like a bunch of other ones as well, which I do want to read. And they are all in chronological order, which is great. So I can go step by step. Hold on. Do they go into any code? No, they don't. Okay. So here they explain the classification side of it, and then shortly after that it ends. Okay. Cool. So I can carry on reading this off stream. Wait, I just realized this thing seems to be a little... Oh no, it's not zoomed in. Okay. The stream is just on a delay. But yeah, okay, I'm getting tired, so I'm gonna end the stream here, and I'll stream day after tomorrow, I think. Yeah, I'll try my best. Now that I'm free from the work that I had to do, I can definitely stream more. And I want to stream more. You know what? If I get a chance tomorrow before my usual stream time, if I get a chance tomorrow, I'll try and stream again. If not, then definitely the day after tomorrow, I'm gonna be streaming. But yeah, that being said, I hope you guys have a nice day, and I will see you all next time. Peace.